Continue on with our discussion of derivatives. I'm going to zoom in since we're a little bit far away to read that. But yeah, we have question 4 says that a mass of m kilograms strikes a cantilever beam with an initial velocity of v0 meters per second. The horizontal displacement in meters of the tip of the beam at t seconds after the impact is given by x of t is v0 over omega sine omega t, where omega is a constant governed by the mass, the length of the beam, and the flexural rigidity of the beam. So we don't have a lot of numbers in this one, we just have kind of variables that we want to talk about. And so we want to determine the maximum displacement of the beam. We also want to comment on what happens on the displacement and acceleration of the beam when the velocity is equal to 0. So we'd set up our equation, we'd set up our sheet, just to give you an idea of what's happening. So we've got some sort of mass in kilograms that's going to hit the beam. So it goes from being a straight beam to it gets deflected this way. And we know because it's a sine wave of the deflection, it's actually going to go this way, then it's going to bounce back, and it's going to just keep kind of shifting back and forth between these two places. And x of t tells us the horizontal displacement at a given time. Of course, we would think if it's bending a lot, you might also have a small amount of vertical displacement, but the horizontal is going to be the much bigger issue. And so, yeah, we define the variables as they define in the problem, and we want to find the maximum displacement. From our previous work on talking about sinusoids, we know that with the sine function, the maximum positive and negative displacement it's all going to be governed by the value of the sine function. So when the sine function is 1, it'd be at a maximum, and when the sine function is -1, it would be at a minimum. But because what we're talking about here is derivatives, is we want to talk about that in terms of setting it up and use derivatives to find our local min and our local max. So again, as we said, we know the maximum displacement would happen when that's equal to 1. We also know that the value equals the amplitude. So we should be able to already determine that the maximum values are going to happen when that is. Using derivatives, we're going to set this equal to 0 instead. So if we use our handy sheet, we know that the derivative of sine omega t is omega times cosine of t, so the omegas would cancel out, and we just end up with for velocity, which is the first derivative of position, is v0 times cosine of omega t. The next step would be to find the places where that equals 0. So v0 is going to be equal to 0, where cosine omega t is equal to 0. And so that means t, if we got out a unit circle, what happened, cosine is 0 at pi over 2, at 3 pi over 2, and we could keep going. It's going to happen again at 5 pi over 2 if we kept going more than one rotation around the circle, and so on. So it's actually going to happen at the time, where omega t is that. But we also want to know part B, is what we're working on here. We want to know about what's going on with the acceleration at those times as well. We know what the function is. We need to know what the acceleration is, which is the derivative of the velocity. So we would take our velocity function, which I should have highlighted here before, or underlined. So that's our velocity function. So when we take acceleration to that, again, we're going to have v0. We're going to get omega out front. When we take the derivative of cosine, we get negative sine omega t. So we're going to get actually negative omega times v0 sine of omega t. It's our acceleration function. So let's take a look at what's happening at those points. So we're going to build this little table to think about what happens to acceleration and position when velocity of t is equal to 0. So we already discussed that velocity of t equals 0, it happens whenever cosine omega t equals 0, or which means that omega t is pi over 2, 3 pi over 2, 5 pi over 2, so on. In other words, at the top and the bottom of the unit circle. Well, if we look at those points, the sine values at pi over 2 it's going to be 1, at 3 pi over 2 it's going to be negative 1, and then it's going to go back to 1 and negative 1, and so it's just going to keep cycling back and forth between those. So if sine omega t is 1, then x of t is going to be v0 over omega. And if it's negative 1, then it's going to be negative v0 over omega. And if it's back to 1, it's going to be v0 over omega. And it's back to negative 1, it's going to be negative v0 over omega. So whenever velocity is at 0, the position is going to be at its maximum stretch, either as far over to the right as it goes or as far over to the left it goes. As if we think of this as our beam being bounced back and forth, when velocity equals 0, it's at that point where it stops and it's turning around and going the other way. By the same token, what's going on with acceleration, if sine is 1, then this is negative omega times v0. If it's negative 1, we're back to positive omega times v0. And then if it's back at positive for the sine, we get negative for the acceleration. And when the sine is negative, we get positive for the acceleration. So acceleration, similarly, is at its maximum levels, just bouncing back and forth at that maximum amount, the amplitude, just kind of on the opposite way. So when we are pushed as far as we can this way, displacement is as much positive as it can be. The acceleration is pulling it back to the left as hard as it can, which makes sense if we think about a beam. The more, if I have a fixed beam down here, then if I'm going out as far as I can this way, if I've displaced it, then there's a lot of force trying to push me back. When I get as far this way to the left, there's a lot of force pushing me to the right. So, so the comment it wants to ask is, we would say that when v of t equals 0, position is at max or min, and acceleration is at, and I guess the way to keep it in mind is at a minimum or a maximum. It's the opposite of 1. Whenever position is at a maximum, acceleration is at a minimum. It's pulling as hard as it can to the left. And so we could graph these different sine waves and see how those work. The other just quick comment to slide in there, we've talked about if x is position, v, which is the first derivative, is velocity. A, which is the derivative of velocity, the second derivative of position, is called acceleration. We just talked about acceleration being at its maximum or its minimum. So there could be some points where we want to keep going past that. If we wanted to find the derivative of acceleration, that's actually uses a j. So it's the second derivative of velocity, the third derivative of position, and they call that jerk. That's why we get a j. And we can keep going past that. or it's also sometimes called jolt. So if you think of a change in acceleration, yeah, it's a jerk or a jolt, a sudden impact to that. If you do the fourth, and it gets really weird to start writing it this way, but 1, 2, 3, 4, which is the third derivative of velocity, the second derivative of acceleration, the first one we have there. They don't really necessarily have one for this one. We'll call it K, I guess. That one is actually called jounce, is the change in jerk, or the change in, or the second derivative of acceleration. And you can keep going. So fifth, let's call it prime 6, and so on. If you keep going, you get to things called like snap, crackle, and pop. And yes, that does sound exactly like the reference here. So, yeah, some engineers or physicists started to really have fun with it as they got past that. But you will see jerk sometimes, the derivative of acceleration. The other ones you just have never actually come up. I've just had to look. You just kind of look them up for fun.